I was born and raised by farmers, but now that I've reached adulthood, I think I'm finally capable of fulfilling my destiny.
Tim Skeks, your father wasn't a navigator on a space freighter. Your father was an elite hacker and a good friend. This is your father's computer, an elegant weapon for a more civilized time. The Empire's devices only run approved software. We need to jailbreak my iPhone from Mad Keks. To assemble a team of more people, we'll need to cut to a bar or something.
So you need to crack your iPhone. Well, the way I see it, there's 3 parts. First, you gotta run the unsigned code outside the sandbox. Second, you gotta get around the kernel address space layout randomization, or KSLR. Third, you gotta take control of the kernel. These things ain't gonna come cheap, if you know what I mean.
The Empire requires that all code running on an iOS device is signed, so software can only come from the Empire's App Store. We need to convince the launch controller to run a program as root, so that it can run our payload and untether the device.
The Apple launch controller manages which programs are run, and as part of Darwin exists on most Apple devices. The launch controller can be used to start launch daemons, processes which run in the background on the iOS device. They're used for applications like Flux and OpenSSH, which depend on running things as background processes.
Yeah, of course I know that. But the security of the launch controller was improved in 6.1. The launcher daemons on the file system are now ignored, and are loaded from the signed dynamic loader cache.
Adding an app requires modifying a particular file which holds the state of all apps, including system apps. Without doing this, we can't run the launch command at all. To modify this file, we can use a combination of 2 services. First, File Relay, which supports copying diagnostic data from a device, can be used to retrieve the file. Second, Mobile Backup 2, a known exploit since iOS 7, makes it possible for apps to write to the var folder, but users could also write to other files simply by using a symlink. Together, these services allow us to modify the file to include our app.
But this hasn't solved the root access problem.
I don't know where you get your delusions, Laserbrain.
Laugh it up, Fuzzball, but you didn't see us alone in the South Passage where Planet Being explained that this could be a legitimate problem.
Why, you stuck-up, half-witted, scruffy-looking nerf herder. There's a line of code in the program lockdown-d which automatically sets the permissions of a system file to 777 without doing any checks and executing every launch. We can pretend that our file is that system file by using a symlink and get full permissions when lockdown-d is crashed and relaunched.
Once we've got root access, we want to disable code signing. We need to make our own configuration file and symlink to it. That way, our launcher would use our new configurations on startup.
You're right, Muscle Nerd. This music is annoying. Let's go somewhere where we can get some peace and quiet.
iOS contains dynamic libraries that are loaded at runtime rather than compile time. They're loaded by the dynamic loader. Another program, Amphid, checks the dynamic library's code signing and tells the dynamic loader whether or not to load it. If we want to run our dynamic library, we need to convince Amphid that our signing is correct.
The dynamic loader handles dependencies and dynamic loading calls. It runs inside the process using it, and uses that process as headers. So it could overwrite MIS validate signature, the function that validates the file's signature, to always return 0, basically disabling code signing.
Of course, the whole code signing design seems so complicated that there had to be a mistake. But how do we get around the KSLR?
We just need to know the address of 1 byte in memory. We can figure out everything else relative to that byte. The function stall type in the USB library does this. It takes an uncasted pointer and causes a userland crash rather than a system crash, so the seg fault is leaked to the user.
Another function, create data, allocates random data. We can predict where it will allocate next, giving us the relative location, and then pass it as a pointer to stall pipe, giving us the absolute location. Boom, there goes Castler.
Of course, a classic error leak exploit. We're uploading it now.